Hai, Assalamualaikum dan salam sejahtera to all my students. Thank you for watching the next video. This is basically our last session for DC bridge, and we're going to talk about Kelvin bridge. Okay? So we're not going to cover mega ohm bridge, okay? Just Kelvin bridge and Wheatstone bridge for DC. Okay, what is a DC bridge? Basically, what is Kelvin bridge? Kelvin bridge is basically a modified version of Wheatstone bridge. Okay. If you look on the right figure here, you can see that originally Wheatstone bridge has 4 resistors, but as you can see, we are now including some extra resistance here. Okay, and we talk about after this. Okay, so it's also called a Kelvin double bridge or Thomson bridge, and the overall operation is pretty much similar. That you can see that in order for the bridge to have a balanced condition, this I of galvanometer must equal to 0. Okay, and other, for example, you have a voltage source here and have the main current coming out here. All right, so overall general operation is quite similar, except for some few modification. So the main purpose of the modification is basically to eliminate the effect of constant lead and contact and lead resistance. Okay, when measuring unknown low resistance. So Wheatstone bridge is good to measure a higher resistance, but when it try to measure low resistance, let's say less than 1 ohm, then this contact resistance will come into play, because contact resistance also very small, but since it compared with small resistance, then the effect we have a large effect on the calculation. So the Kelvin bridge basically can be used to measure an unknown low resistance, let's say between 1 micro ohm to approximately 1 ohm. Okay, so very small resistance, then it's better to have a Kelvin type of bridge. Okay, so basically I'm not going to go through the derivation, and I think I'm just going to go straight forward to how are we going to use. So this is basically the setup that you need to remember, and how to use the formulation later on I'm going to show you. So the arrangement is such that, okay, you have a main resistor here, R1, R2, and R3, and Rx. It can be R4. It can be any number, A, B, C, or X, Y, Z, up to you how you're going to label it. But actually, you have to remember the position of each resistor according to the formula that I'm going to give you. Okay, so let's, the first thing I want to show you that the resistor RLC here, which is here, okay, represent the lead and contact resistance present in the Wheatstone bridge. This is a contact, basically the wire where it connects from, let's say, from galvanometer to another resistor. Okay, so basically the lead and also the line. The lead basically is the wire, the wire that connect from one point to another point. That also contains some resistance, a very small resistance. Okay, so you want to model that to include that resistance. Okay, in the circuit. Okay. And the second set of ratio arms, RA and RB. So you can see that there is this additional RA and RB is inserted into the second arm. Basically, it is used to compensate for the relatively low lead contact resistance. Okay, so this is for the higher ones, and RA and RB is a lower kind of value of resistance. So basically, RA, RB, and RC is basically is inserted into the Wheatstone bridge in order to counter the small amount of area presented by the lead resistance. So okay, so because of that, so at balanced condition, if you want to include RA and RB, okay, this is basically to come up with this point here, it requires a lot of derivation, but we are not going to cover that in this course. I'm just going to go simply straight to the point. Okay, just remember that at balanced condition, the ratio of RA to RB, RA is the RA and RB, RA is to RB, must be equal to the ratio of R1 to R2, meaning that, okay, RA to RB is equal to R1 to R2. Okay, remember that where is RA? RA is here, and R1 is here, and R2 is here, and RB is here. Okay, so remember that the position of the resistor, it must be equal, must match this equation. Let's say for example, you see an example of problem that you have a different value, which is R3, which is R4, which is R6, or whatever number you want to put it. but please make sure that this the position is correct according to this figure. Okay, it can also be shown that when a null or balance exists, and same right here, the value of the unknown resistor, which is now call it Rx, is the same as that for the Wheatstone bridge, which is Rx multiplied by R2 equals R1 multiplied by R3. So Rx basically multiplied by the opposite arm, equal to R1 divided by the R3 at the opposite arm. So this one opposite, one's opposite. So you can also change the equation. If you are given, let's say, R1, R2, and R3, you can solve for Rx in this way. So if we combine equation number 1 and equation number 2, we can relate between the unknown resistor Rx into the equation in the resistor Ra, Rb, and the R3. So as I mentioned before, this equation only unique for the diagram that I've shown this here. If you have a different diagram, maybe from other different textbook, then you have to follow a different set of equations. So you can change the equation into this one. You can manipulate that into equation number 4. Alright, let's take a look at one example here. In the figure here is given that the ratio of Rb to Ra is 1000. This is 1000. This one, I think just eliminate that. R2 is given to be 5 ohm, and R2 5 ohm, and basically this, and this R ratio between R2 is equal to 0.5 multiplied by R3. This is given in the question. So now let's find, let's use the previous formula that we give you and find the value of Rx. So how to solve that? So it's given that, Rb to Ra is 1000, the ratio, or we can say that Ra to Rb is equal to 1 over 1000. Since it's also that given that R2 equals to 5 ohm and R2 equals 0.53, we can solve for R3, which is R2 divided by 0.5. Just use this equation here, and we insert R2 equals 5 ohm in here. And we got R3 equals to 10 ohm. Very simple. Therefore, Rx can be calculated as follows. So we know that Rx equals to Ra divided by Rb multiplied by R3. So, and then it's 1 over 1000. Ra to B is this one. 1 over 1000. We put back into this equation here. Multiplied by R3 that we have calculated just now. And you get Rx equal to 0.01 ohm. It's very small. Around 10 milliohm. Alright. So I think that's all I'm going to say, discuss about Kelvin bridge. If you have any question, please put it online, post that question online in WhatsApp group or in the ULearn or in the YouTube channel that I have set up for you. So thank you very much. Thank you for listening. I'll see you again on our next chapter on AC bridges. Have a nice day. Assalamualaikum.